Welcome to Statistics, where we bring complexity to clarity. I am excited to have you join me for our 16th unit chi-square test. Let's begin with a brief introduction. T, Z and F tests are to be utilized for testing the parametric hypothesis like H0 mu1 is equal to mu2 or H0 sigma 1 square is equal to sigma 2 square, etc. for the quantitative information or measurement data. The hypothesis of qualitative or enumeration information can be tested by chi-square test, where the observed frequency distribution is to be compared with the hypothetical or expected frequency distribution. The chi-square statistic compares the tallies or count of categorical responses between two or more independent groups. Chi-square test can only be used on actual numbers and not on percentages, proportions, means, etc. Chi-square was introduced by Karl Pearson in the year 1899. It is defined as the test we use to measure the differences between what is observed and what is expected according to an assumed hypothesis is called chi-square test, or it can be defined as the sum of the ratio of the square of deviations obtained between observed and expected frequency to the expected frequency of the respective class of the distribution. And it can be symbolically written as chi-square is equal to summation I is equal to 1 up to k oi minus ei square divided by ei, where oi is the observed frequency of ith class, ei is expected frequency of ith class, and k is equal to number of classes, where I is equal to 1 to up to k. Now let's discuss the properties of chi-square distribution. Chi-square distribution is not exact distribution as T distribution. It is not symmetrical distribution but is positively skewed distribution. The value of it varies from 0 to infinity, that is, it considers only positive values. When there is a perfect agreement of observed frequency distribution with hypothetical frequency distribution, the value of chi-square will be 0. That is, as we know that it is the ratio of difference between observed and expected frequency squared to the expected frequency. So here the difference is 0, hence the value of chi-square will be 0, while the value of it increases as there is departure from the agreement and will be increased up to infinity. Hence, if the difference is increased, then the chi-square value will tend to infinity. If chi1 square, chi2 square, chi-k square are chi-square values of different samples with n1, n2 up till nk degrees of freedom respectively, the pooled chi-square value will be equal to chi-p square is equal to summation I is equal to 1 up to k chi-i square with n is equal to summation ni degrees of freedom. Now let's see the fourth property with the help of example. Suppose chi1 square is equal to 10, chi2 square is equal to 15 and chi3 square is equal to 20, and their respective degrees of freedom n1 is equal to 5, n2 is equal to 6 and n3 is equal to 7, then the pooled chi-square, chi-p square is equal to 10 plus 15 plus 20 is equal to 45, and the degrees of freedom will be summation ni, which is equal to 5 plus 6 plus 7, that is 18. Hence, we have to check the chi-square value 45 at 18 degrees of freedom. As the number of observation tends to infinity, the chi-square distribution tends to normality. Now let's see the conditions for applications of chi-square. Deviations oi minus ei should be normally distributed. Number of observations should be sufficiently large. It should be at least 50. Expected frequency of any cell should not be very small. It should be at least 5 and better if it is 10. The constraints or restrictions which are to be imposed should be linear. Now let's see the uses of chi-square. Chi-square is used to make a test of goodness of fit, to test the independence of attributes, to test whether a hypothetical value sigma 0 square of the population variance is true or not, to test the validity of hypothetical ratios, to test the homogeneity of several population variances, and to test the equality of several population correlation coefficients. Now let's discuss the first use, that is testing goodness of fit in detail. When chi-square test is used to know whether the given sampling distribution is in agreement with the theoretical or expected frequency distribution, the test is known as test of goodness of fit. Let's see the procedure for testing goodness of fit in stepwise manner. The first step is set the appropriate null hypothesis, that is H0 is equal to given sampling distribution is in agreement with theoretical or expected frequency distribution, and alternative hypothesis will be given sampling distribution is not in agreement with theoretical or expected frequency distribution. Step 2 is fix the level of significance. Usually 5 and 1% levels of significance are fixed. Step 3, work out expected frequency according to given ratio or expectation. Step 4 is to calculate chi-square using the formula chi-square is equal to summation I is equal to 1 up to k oi minus ei square divided by ei, where the variables are as given. Step 5 is conclusion. Compare calculated chi-square with table value at 5% level of significance and k-1 degrees of freedom. If calculated chi-square is less than table chi-square at 5% level of significance and k-1 degrees of freedom, then observed difference is not significant at 5% level of significance and H0 is accepted. Acceptance of H0 means the given sampling distribution is in agreement with theoretical distribution and the fit is good. Whereas if calculated chi-square is greater than table chi-square with k-1 degrees of freedom, then observed difference is significant at 5% level of significance and H0 is rejected. Rejection of H0 means the given sampling distribution is not in agreement with theoretical distribution and the fit is poor. Now let's see the second use of chi-square, that is test of independence of attributes in details. For it, let's check out some of the terminologies associated with it. Independence. The two attributes A and B are said to be independent to each other if the proportion of A's among B's is the same as that in not B's. Variable. Any character which is varying from individual to individual is termed as variable. Attribute. Attribute is that which is not capable of being described numerically, example, gender, blindness, color, shape, etc. Contingency table. A contingency table is a two-way table in which the columns are classified according to one criteria or attribute and rows are classified according to other criteria or attribute. Each cell contains that number of items Oj possessing the qualities of the ith row and jth column, where I is equal to 1 2 up till m and j is equal to 1 2 up till p. In such a case, the contingency table is said to be of order m cross p. Now let's see the procedure for test of independence of attribute for 2 cross 2 contingency table in stepwise manner. The first step is to set the appropriate null hypothesis, that is H0 will be attributes A and B are independent, and alternative hypothesis HA will be attributes A and B are associated. Step 2 is to fix the level of significance. Usually 5 and 1% levels of significance are fixed. Step 3. Let group A and B are classified in two ways. The results of the classification can be set out the following contingency table. Now let's understand the 2 cross 2 contingency table. Here the values A, B, C, D indicate the observed frequency. R1 and R2 indicates the row frequency or row total. C1 and C2 indicates the column frequency or column total, and capital N indicates the grand frequency or grand total. Step 4 is to calculate chi-square, as chi-square is equal to AD minus BC square into capital N divided by R1 into R2 into C1 into C2, and degrees of freedom will be R minus 1 into C minus 1, which is equal to 2 minus 1 into 2 minus 1, that is 1. You can put the variables in the given formula from the given table. Step 5 is conclusion. Compare calculated chi-square with table value at 5% level of significance and 1 degree of freedom. If calculated chi-square is less than table chi-square at 5% level of significance and 1 degree of freedom, the observed difference is not significant at 5% level of significance, and H0 is accepted. Acceptance of H0 means the two characters are independent to each other. Whereas if calculated chi-square is greater than equal to table chi-square at 5% level of significance and 1 degree of freedom, the observed difference is significant at 5% level of significance, and H0 is rejected. Rejection of H0 means the two characters are associated. Now let's see the procedure for test of independence of attributes for 2 cross C contingency table in stepwise manner. The first step is same, that is, set the appropriate null hypothesis H0 as attributes A and B are independent, and alternative hypothesis attributes A and B are associated. Step 2 is fix the level of significance, that is usually 5 or 1%. Step 3 is let a group of individuals is classified in two ways in 2 rows and C columns in the following contingency table. So here there are 2 rows and C columns. Step 4 is to work out expected frequency of each cell as follows. Here E11 is equal to R1 C1 divided by capital N, E12 is equal to R1 C2 divided by capital N, and E1j is equal to R1 Cj divided by capital N, and similarly for E21, E22 and E2j. The next step is to calculate chi-square using the usual formula of chi-square. And the sixth step is conclusion. Compare calculated chi-square with table value at 5% level of significance and 2 minus 1 into C minus 1 degrees of freedom. If calculated chi-square is less than table chi-square at 5% level of significance and 2 minus 1 into C minus 1 degrees of freedom, the observed difference is not significant and H0 is accepted. Acceptance of H0 means the two characters are independent to each other. Whereas if calculated chi-square is greater than equal to table chi-square, then the observed difference is significant and H0 is rejected. Rejection of H0 means the two characters are associated. Now let's see the procedure for test of independence of attribute for R cross C contingency table in stepwise manner. Here the first step is similar to 2 cross 2 or 2 cross C contingency table, that is, set the appropriate null hypothesis as H0 and HA as given. And step 2 is also same to fix the level of significance, usually at 5 or 1%. Step 3 is let a group of individuals be classified in two ways in R rows and C columns in the following table. Here, as you can see, that there are C columns and R rows. Fourth step is to work out expected frequency of each cell as follows. Here E11 is equal to R1C1 divided by capital N, E12 is R1C2 divided by capital N, and E1J is R1CJ divided by capital N. And similarly for E21, E22, E2J, also for EI1, EI2 up till EIJ. Hence, in general, EIJ is equal to Ri into Cj divided by capital N. Step 5 is to calculate chi-square using the usual formula of chi-square, that is, chi-square is equal to summation I is equal to 1 up to k oi minus ei square divided by ei, where the variables are as shown. And the sixth step is conclusion. Compare calculated chi-square with table value at 5% level of significance and R-1 into C-1 degrees of freedom. If calculated chi-square is less than table chi-square at 5% level of significance and R-1 into C-1 degrees of freedom, then observed difference is not significant at 5% level of significance and H0 is accepted. Acceptance of H0 means the two characters are independent to each other. Whereas if calculated chi-square is greater than equal to table chi-square, observed difference is significant at 5% level of significance and H0 is rejected. Rejection of H0 means the two characters are associated. Thank you for joining me on this journey through our 16th unit chi-square test. If you found this unit helpful, don't forget to like, share and subscribe to Statistics for more insights and clarity on statistics. Your support helps us continue creating content that makes complex topics simple and accessible. Follow us on Instagram and LinkedIn.